A $680 million survey telescope with a 3.2 gigapixel camera spent over 6 hours imaging one region of the Milky Way. So what did it get? Today, let's break down this Rubin Observatory image of M8 and M20. You've probably seen this image already, but don't scroll away yet. This is not just another image review, and I'm not going to repeat the press release. We'll take it apart and see how powerful a top ground-based survey telescope can be even under Earth's atmosphere. Over 4 billion pixels, one file, 26 gigabytes. And yes, Rubin really spent serious resources on this image. How much did it cost? I'll answer that at the end.
Hi everyone, I'm Ethan. Welcome to my channel.
First, the equipment. This image comes from the system many people still call LSST. Think of it this way: a giant 3.2 gigapixel camera with a focal plane about 64 centimeters wide, mounted behind an 8.4 meter f1.23 telescope with an 8.4 meter aperture and a 9.9 meter focal length. You might think this is a super telephoto system, but in astronomy, it is more like a giant format wide-angle camera. Now let's look at M8 and M20. This image covers about 4.67 by 2.86 degrees, roughly 9 full moons across. In full-frame terms, that is similar to a 450mm lens, a classic bird photography focal length. The final image is over 4.3 billion pixels, about 84,000 by 51,500. The file is over 26 gigabytes. I tried several image viewers. Only Photoshop could open it, and editing was almost impossible. This is not a normal photo anymore. It feels like a zoomable map of the universe. But the raw data is much larger. This image was built from about 664 exposures through different filters. Together, that is about 2 trillion pixels. Behind this 26 gigabyte final image, there are terabytes of raw data. Our 52 C-star array produced about 200 gigabytes. Here, that almost feels tiny. The data is sent from Chile through a high-speed network to the SLAC data center in the US for processing, image comparison, and transient alerts. That is a national-level astronomy data pipeline. When astrophotographers hear multi-channel image, many will think,
Okay, RGB.
but this is not a normal LRGB image. Rubin uses scientific filters, U, G, R, and I. U is near ultraviolet, G is blue-green, R is red, and I is closer to near-infrared. That is why the color looks different from the images we usually process. The G, R, and I exposures were about 30 seconds each. The U exposures were about 38 seconds. With an f1.23 system, it really does not need long single exposures. Now let's zoom in and see what it actually captured. M8, the Lagoon Nebula, and M20, the Trifid Nebula, are targets many astrophotographers have already imaged. And because they are so familiar, the power of a top-tier survey telescope becomes much easier to see. Let's look at a few details that are usually hard to observe. First, the jet structure inside M20, the Trifid Nebula. Hubble has photographed this region too. Inside M20, a cloud of gas and dust is being torn apart by intense radiation. From the top of that cloud, you can see a thin jet. NASA says these jets are about 3/4 of a light year long and are being eroded by nearby massive stars. So these two images give us a great Rubin versus Hubble comparison. The result is clear. For local resolution, Hubble is still far ahead. It is in space, so there is no atmospheric blur. Rubin is ground-based with no adaptive optics, but Rubin has one huge advantage: field of view. Compared with this Hubble close-up, one Rubin exposure covers roughly 400 times more sky. So Hubble gives us the close-up. Rubin gives us the wider Milky Way context. The second detail is HH870 near the center of M8. M8 is not just a beautiful red nebula. Near its central hourglass region, there is an object called HH870. HH stands for Herbig-Haro object. In simple terms, it is a glowing shockwave created when a newborn star shoots high-speed gas into the surrounding nebula. So HH870 is not just a star-like dot, it is a trace of star birth. In this Rubin image, we can easily locate the HH870 region and even see faint structure near the suspected young star behind the jet. Billions of years ago, our sun may have gone through a similar jet phase. The third detail is PK006-02.1. Most astrophotographers have probably never heard of it. It is a tiny planetary nebula near this region. A planetary nebula has nothing to do with planets. It is the remains of a sun-like star near the end of its life. In many wide-field images, PK006-02.1 looks like a tiny blurry dot, easy to mistake for a star or simply ignore. But in this Rubin image, it is clearly resolved. In one image, we see jets from newborn stars and the remains of a dying star. That is what makes this field so interesting. Besides that, near M8, you can also see the globular cluster NGC6544. It is not floating alone against a black background. It is embedded in the dense Milky Way star field. Next to M8, there is also a beautiful nebula region, including NGC6559, IC4685, IC1274, and IC1275. After the details, let's talk about its resolution. First, zoom into the Milky Way in the lower left corner. At first, it looks like a cloudy glow, but at full scale, that glow breaks into countless stars. Every tiny point here is a star. This is what makes the vastness of the Milky Way feel real. The image scale is 0.2 arcseconds per pixel. With a high-resolution full-frame camera, you would need about a 4,000mm lens to reach similar sampling. But with that focal length, the full-frame field of view would be extremely small. Rubin's power is that it spreads this sampling across a huge 64cm focal plane, while still covering a very wide field. Of course, 0.2 arcseconds per pixel does not mean true 0.2 arcsecond resolution. It is still a ground-based telescope limited by Earth's atmosphere. Rubin's median atmospheric PSF is about 0.67 arcseconds. For a ground-based wide-field telescope with no adaptive optics, that is already very impressive. More importantly, this image quality is not limited to the center. Even near the edges, the stars still look excellent. I also found some great images taken with professional-level amateur setups to compare with Rubin. Of course, just treat this part as a fun comparison. Finally, let's estimate how much this image cost. A telescope at this level rarely spends this much time on a common nebula region just to make a showcase image. This data was taken over 4 nights. The total observing time was about 7.2 hours, with just over 6 hours of open shutter exposure. So how much is 7.2 hours of Rubin time worth? Rubin is not a commercial rental telescope, so there is no official hourly rate. We can only make a rough estimate. Rubin's annual operating cost for its first full year is about $72 million. If we assume 250 effective observing nights per year and 8 hours per night, that gives about 2,000 observing hours per year. So the operating cost is roughly $36,000 per hour. For 7.2 hours, that is about $260,000, and that is only the telescope operating cost. It does not include processing or other hidden costs. So this is just a rough estimate. If you have a different way to calculate it, tell me in the comments. This is a world-class survey machine spending almost an entire night to create one map of the universe. And this is only the beginning of the Rubin survey era. Over the next 10 years, it will scan the southern sky again and again, searching for asteroids, comets, supernova, variable stars, distant galaxies, and maybe things we have never seen before. If you are still watching, thank you so much. This channel will keep making serious astronomy content, not just beautiful images, but also the instruments, technology, and science behind them. If you enjoyed this video, please like, subscribe, and turn on the bell. It really helps the channel. And if there is another observatory image you want me to break down, leave a comment below. See you next time. Bye bye.